Alrighty, good morning. Algebra 2, this is period A1. This is, what is this? This is Tuesday, May 26th. My day is all thrown off because of Memorial Day weekend, but I do hope that you had a fantastic Memorial Day weekend and are now ready for essentially the home stretch. This is it. We got this the rest of this week. We got one more full week, and then we have just our little, I think, 2 or 3 day week after that, and the school year is over just like that. It seems like, there's sometimes, especially when you're in like January or maybe February, when there's like hardly any breaks thrown in there, where you're like, oh, geez, this year seems to be dragging out forever. But just like that, you blink and we're right at the end. So it's been a crazy end to the year. It's definitely an unprecedented end to the year, but I appreciate all of your hard work and dedication, and I want to emphasize the fact that we should end strongly and not just go out on a whimper. All right, so we're going to try to really end on a high note today. What I had to do for you guys is a little unplanned because last Friday, you'll probably hear this from literally every teacher today. Last Friday was the catch-up day right before Memorial Day weekend. We did not know that that was going to be the case until, kind of the last minute. So, of course, I sent out a schedule email for you guys in the morning, and I was like, this is going to be our schedule going forward, and I was so happy because everything was organized, and then it was like, nope, that is definitely not happening. So I did have to send out that progress assessment to you prior to Memorial Day weekend. It was sent on Friday morning. It is just more rational equations. The reason why I decided to do that is because, again, you had that whole Friday to work on it. It's only 4 problems, and it is stuff that you should be comfortable with already. It's not any material that we have yet to cover. The last day, which will kind of go, that it never really happened, was just to reinforce those concepts. It wasn't really to teach anything new. So if you need a refresher on rational equations, please go back and watch the rational equations videos. If you did not get a chance to do that PA, please, please, please make sure you get it to me. It's the 4th PA. Make sure you get it to me by the end of the day today, if possible. If you really needed to get it to me tomorrow, I guess that's fine. I plan on looking at it tomorrow night, so please make sure you get that to me as soon as you can. All right, I know that kind of came as a surprise, and I felt bad that I kind of had to do that, but with the way the schedule got shifted, I didn't really have a choice if we want to get in 5 grades before the end of the year. Speaking of which, what we're going to, so again, I apologize, but hopefully you understand why that's the case. And some of you already did the PA, so that's fantastic too. Speaking of which, what we're doing before the end of the year, we really only have one big topic left, and that is word problems. These word problems of rational equations can be tricky. All right, they're not as straightforward as they seem. But the reason why we really emphasize them is, number one, because they do use our rational equation concepts that we talked about in class. And number two, these are prime time SAT style questions that you would see on any sort of standardized assessment like that. All right. They love questions like these. I actually kind of like questions like these because these are pretty realistic things that are used in real life. Maybe not this black and white as you'll see in these problems here, but definitely these concepts come into play a lot. So I think it's really worth taking the time to explore. So that's what we're really going to be doing for the rest of the year. We'll probably do a little bit of Algebra 2 review towards the end. Not that you have a final exam this year, but just to sort of refresh you on the concepts that is expected for an Algebra 2 student to know after this class. What I plan on is essentially taking those last few days in June and saying, all right, as a student who has now successfully, hopefully, completed Algebra 2, this is what you should know going into pre-calculus or going into whatever your math career takes you or wherever life takes you after this. This is definitely the key takeaway topics that you should be comfortable with. All right, so we'll get to that later. But right now, we have some word problems. Just a little quick reminder, we have our word problems today and on Thursdays the next time we see each other, so we will have word problems on both of those days. After that, I do plan on sending out a progress assessment. It will be the last progress assessment required for seniors to complete. It will be sent out on, I'll probably send it out after class today, actually, just in case some seniors want to get a head start on it and get it completed before Friday, because Friday is the last day for seniors, and we do have a couple seniors in here, which is fantastic. So I will probably send it out today just in case they want to get it completed. The official due date is going to be Sunday night. I believe that's May 31st. I can double check the date on that really fast. It is May 31st. So that will be the official due date. That will be the last progress assessment for seniors, but I will send it out after class today. It will be on these word problems just in case they want to get a head start on it. All right. So that's it. that's all the framework and all the introduction that I wanted to give. Again, I apologize for sort of springing that PA on you last week, but it was what was necessary in order to get the grades in, given the schedule change and given the fact that we only meet in a limited amount of time. All right, enough about that. Let's actually go in and jump into word problems. All right, so with these word problems, just sort of a little preface before we actually jump in. With these word problems, we are going to be focusing on 3 categories. Okay? All of which apply our knowledge of rational equations. The first category is something that I like to call a distance, rate, and time problem. Okay? Distance, rate, and time problem. The way that distance, rate, and time problems works is it's an application of physics. It goes back to, you may actually remember this little triangle diagram from physics first. I don't know if you remember this. That's like D is on top and R and T is over here. It all goes back, it's something like that, right? It all goes back to this formula that in physics, the distance that something has traveled for is equal to the rate at which it traveled divided by time. Distance is equal to rate divided by time, right? Is that true? Or is that distance equals rate times time? I think that's distance equals rate times time. Distance equals rate times time. Not R over T, right? D equals RT. Holy jeepers, it's been a long weekend. It all goes back to this formula of the distance that something let's try that again. It all goes back to this formula that the distance is that something traveled is equal to the rate at which it travels times the time. If something is traveling for 3 miles an hour and it travels for 5 hours, well, then it's traveled a total of 15 miles, right? Whew, that makes a lot more sense. Holy cow. A lot of people probably just got really confused, myself included. But the distance at which something travels is equal to its rate times its time. That's what this little diagram is supposed to be. Come on, Mr. Giorgio. This is physics first here. But from this formula, there's actually a couple variants. Of course, you can also say, just by rearranging the formula, that the rate at which something traveled is the distance divided by the time. If you took this formula and divided both sides by t. And the time at which something traveled is the distance divided by the rate. Okay, so this one formula from physics, that distance equals rate times time, has sort of 2 variants to it, making a total of 3 formulas here. Depending on which one of those pieces of information we're given, that's the formula that we're going to use. Okay, if we're given the fact that the distances are the same, we're going to use something like this. If we're given the fact that the rates are the same, if we're given the fact that the times are the same. Okay, so our first category of word problem uses this relationship from physics first, that the distance is equal to rate times time, or the variance of that, rate is equal to distance divided by time, or time is equal to distance divided by rate. The second variant is what's referred to as a work done problem. Okay, and what that essentially, the way that this essentially works is it's multiple people, machines, things, animals, it could be whatever, multiple things working together to accomplish a similar task. They're working together to accomplish a goal. That's how work done problems are really done. And the way that these are actually, the kind of the formula for these types of problems, the way that these are actually done, is you would say that this is somebody's rate per unit of time times their time contributed plus. And then you kind of do that for each one of the things that are working on the particular task. For example, if there are two people working together to build a house, that's the example that we're actually going to look at today, then you would take the first person's rate per unit of time. And what that means is if it's just per minute, per second, per hour, whatever measurement of time that this problem happens to be presented in, times the time that that person contributed to the project. Then you would add with that the next person's rate per unit of time times their time contributed. If there were 3 people, you would then add another one, rate per unit of time times time contributed, and altogether these would all be equal to 1, because the value of 1 would represent 1 task completed. Okay? So all this rate per unit of time times time contributed plus rate per unit of time times time contributed, this is done for each person. I'll just say person, but it could be machine or whatever, working towards the goal. Okay. Again, it doesn't necessarily have to be people. It could be that 2 machines are doing something at a certain rate, and it seems how fast is it going to take, how long is it going to take for them to actually accomplish their goal. But it's for each entity, I guess that would be a better word, for each thing working towards the goal. And last but not least, what we have here is we have a little bit of application of chemistry called solution or mixture problems. Okay. Don't worry, we're not delving into stoichiometry and all that crazy madness. What we are doing, however, is we're essentially saying that the first mixture, mixture number 1, plus any second mixture should be equal to the final mixture. Essentially, the questions that these problems will pose is you have a certain amount of a certain solution that is given to be a certain concentration of a material. For example, the one we're going to look at says you have, what does it say? How many grams? 120 grams of a 40% salt solution. And how many grams of a 10% salt solution must you add in order to get a 30% salt solution? I forget if that's the actual goal, but that's sort of the premise where we say, okay, I have my first mixture. How much of this mixture should I add to that to obtain a mixture that I desire? All right. I know just looking at it from an overview perspective, it can seem a little confusing and vague, but when we delve into some specific examples, I think it will make a lot more sense. All right, so let's do that right now. Our 3 categories in order, we have distance, rate, and time, we have work done, and then on the back of this page, we have a solution and mixture problem. Again, in case you're struggling to read the words on this paper, I did post the typed copy on Google Classroom, so you can follow along with that. This first problem says 2 cars drive at the same rate. One car drives 180 miles and the other drives 270 miles. If the first car drives for 2 less hours than the second, how long did each car drive for? Well, without me having to tell you, hopefully if you look at this problem, you would be able to identify that it is a distance, rate, and time problem because it talks about distances, rates, speeds, how far did each car drive, it's cars moving. Like, that should just make sense to you to say this is a distance, rate, and time problem. So I'm not going to specifically say, oh, this problem is distance, rate, and time. You should be able to identify that based on the scenario and the language of what's going on. So the way that I like to organize this is, first of all, identify which of these pieces of information is equal, correct? Does it make sense that say that 2 cars drive at the same rate, right? So it should make sense that the rate of car 1 should equal the rate of car 2. This is how we can start to translate into an equation. Well, how do we find the rate? We just said over here that the rate that something travels is equal to its distance divided by time. So I can say over here, well, the distance divided by the time of the first car should equal the distance divided by the time of the second car. Okay? Maybe you can denote it with a little subscript 1. D1 over T1 equals D2 over T2. Okay? So let's see if we can actually just fill in that information and go from there. All right, let's see if we can fill in that information and go from there. What is the distance of the first car? Well, it says one car drives 180 miles, so I guess I'm going to substitute that for distance. We're going to say that the first car was 180 miles. The other car drives 270 miles. I'm just trying to fill in the information that's given. Do you guys see that? Because we identified two cars drive at the same rate, that's what led me here. We know that rate is distance divided by time, so now I'm just filling in the information accordingly. It now says if the first car drives for 2 less hours than the second, or 2 fewer hours, I think might be the proper English there. But 2 fewer hours than the second, how long did each car drive for? Well, that's great. We can say that this car drove for 2 less hours than this one. Well, how long did this one drive for? The answer to that is we don't know. So the way that I could denote this is I could say, well, the second car drove for X number of hours. And if this drove, the first car was 2 less hours, then I would say that this is X minus 2. Do you see why that's the case? The first car drives for 2 less hours than the second, so we don't know how long the second car was driving for, but we do know this one was 2 less than however long that was. Hopefully that makes sense, yes? And now, this is a good old rational equation that we could go ahead and solve for x, and then apply it to the problem to find out how long each car drove for. So I can now say that my least common denominator here, I need a factor of x, and I need a factor of x minus 2. That makes this happy and this happy, just like our equations from last week, right? Notice that we don't have to identify extraneous solutions here. Given that this is a real-world application, it wouldn't even make sense to get any extraneous answer. You certainly can if you want. You certainly can say that x should not equal 0 and x should not equal 2, which is absolutely correct, but it's not necessary. Now that I have my least common denominator, we can go ahead and convert our denominator here and convert our denominator here. What do I need to multiply this by in order to get this? I need to multiply by x. So I'm going to take the top and multiply by x. What do I need to multiply this by in order to get this? I'm missing the x minus 2, so I'll take the 270 that's already there and multiply by x minus 2. This is just what we did last week. Okay. Now your denominators are the same, so we can just focus on those numerators, giving us 180x equals, a little distributing here, 270x, and then minus, what is that? That is 540, I believe. Okay. And now, bigger numbers than you may be used to working with, but this is really just Algebra 1 at this point. Continue right up here. I can subtract 270x from both sides. You get negative 90x equals negative 540. And so, dividing both sides by negative 90, you get x is equal to 6. So, it would be very tempting at this point to stop, but x equals 6 does not actually answer the question. The question was asking, how long did each car drive for? Well, if x equals 6, then that means the second car drove for 6 hours, correct? So you'd say car 2 drove for 6 hours. But therefore, how long did car 1 drive for? It drove for 6 minus 2 hours, or 4 hours. So car 1 drove for 4 hours. And that would be your acceptable solution. Okay? Does anyone have a question on any of those problems, or anything about this problem? Okay. One thing specifically that I want to point out is the fact that this equation got started by saying that 2 cars drive at the same rate. If it said 2 cars drive for the same amount of time, well, then we're going to say the time of the first car should equal the time of the second car, meaning that we're looking for distance divided by rate. If it said that the distances are the same, well, then we'd say distance of first car equals distance of second car. It's not even really a rational equation at that point, because now it's rate times time here equals rate times time here. Okay? So just be mindful of trying to identify which of those aspects are equal. That's what makes your equation, and then you can go from there. All right, going into the next problem. Ready? It takes Gary's construction company 27 days to build a house. if Gary's construction company and Larry's construction company worked together, they could build the same house in 10 days. How long would it take Larry's construction company to build that house alone? All right. So this requires a little bit of thought. Notice we have Gary and we have Larry. Okay. I want to keep track of, given that this is a work done problem, hopefully you can make that assumption because it's two people or things working together to accomplish a task. I want to keep track of their rate per unit of time as well as their time contributed towards the project. Okay, so there's two pieces of information I want to keep track of. I want to keep track of their rate, per day in this case, because that's the unit of time. And I also want to keep track of their time contributed. Okay, so I'm going to make a little table to help organize my information. So let's start with the rate per day. And this is a different sort of mindset that you have to think about. If it takes Gary's construction company 27 days to build a house, you may be very tempted to say, oh, well, the rate is 27. It takes 27 days. Not the case. If it takes 27 days to build a house and you're working at a constant rate, how much of that house is completed per day? That's the question that you're really trying to answer. And the answer to that question is 1/27th is completed per day. Think about it. If it takes you 5 days to write an essay, for example, for English class, how much of, and you're working at a constant rate, you don't procrastinate and save it all till the end, which I know you don't do anyway, but just saying, how much of that essay gets completed per day if you work at it at a constant rate? Well, 1/5 of it would get done the first day, and then another 1/5 and another 1/5. It would take 1/5 of the essay per day. The same exact thing is true here. If it takes 27 days to complete the task, then every day 1/27th of the task is getting done, so that by the end of the 27 days it would be all done. Okay. It then says if Gary's construction company and Larry's construction company work together, they could build the same house in 10 days. So their time contributed for both of them, if they're both working together, they could get the house done in 10 days. So I would say they're both working together for the entirety of 10 days. If Gary contributes 10 days and Larry contributes 10 days, then the house gets done. So how long would it take Larry's construction company to build that same house alone? That's what we don't know. We don't know Larry's rate per day. So we would assume that it takes him X number of days, an unknown number of days, to build the house alone. So we would say that his rate was 1/x. 1/x, just like that. Think about it. If it took him 3 days to build the house alone, that would be very fast. But you would say, oh, well, then every day, 1/3 of it is getting done. If it takes 7 days, then every day, 1/7 of it gets done. If it takes X days, then every day, 1/x of it is getting done. Does that make sense to everybody? It's a little different way of thinking, but hopefully it's a little logical. Now I would say here, well, I have Gary's rate times his time contributed plus Larry's rate times his time contributed should equal the whole house being built. So that's exactly how I'm going to make my equation, just like I said over here. Rate per unit of time times time contributed plus the next rate per unit of time times time contributed, and so on and so on and so on, equals the full task completed. All right, so I would say that Gary's rate of 1/27 times 10 days plus Larry's rate of 1/x, which we don't know, times 10 days should equal the full house getting completed. Now, I don't think you'll be presented with a problem like this. In fact, I know you won't. But what if the problem said, how long would it take him to build 2 houses? Well, then you would just say it equals 2, because your task would now be, it would really be 2 tasks, right? But all these problems are just going to say how long does it take to accomplish one thing. You don't have to worry about that. But if it did, if you encountered one in the wild world of mathematics, it wouldn't be, hopefully, very confusing. Now you can go ahead and solve this. If I multiply here, I get 10/27 plus 10/x is equal to 1. I can now find my least common denominator. My least common denominator here would be 27x because I need a factor of 27, a factor of x. Now, when you convert, do not forget the most common mistake students make on this is forgetting to convert the 1 at the very end. Please do not forget to do that. I'd like this to be 27x, I'd like this to be 27x, and I'd like this to be 27x. So what do I need to multiply this by to get this? I'm missing the x, so that's what's going to go here. What am I multiplying this by to get this? I'm missing 27, so I'm going to do 10 times 27. And what am I multiplying this by to get this? The whole thing, 27x. And so ultimately, just finish right up here, the denominators are the same. We don't have to account for them anymore. I get 10x plus, that's 270, is equal to 27x. I can subtract 10x from both sides, gives me 270 equals 17x. And if I divide both sides by 17, let's see, 270 divided by 17, it looks like we get about 15.88. Okay. And so you would say that it takes Larry's construction company 15.88 days, approximately just about 16 days, to do the house alone. Okay. Any questions about that problem at all? All right, bear with me for a couple extra minutes. I would like to present this problem to you, the last one. Okay, solution mixture, at least set it up. So it says a container currently has 120 grams of a 40% salt solution. How many grams of a 10% salt solution must be added to that to obtain a 25% salt solution? I like these problems a lot because they're very logical to me. If you have one solution and you're trying to get a final solution, what do you need to mix together to make that happen? Okay, the way that I would word that is I would say my first mixture, mixture number 1, plus my second mixture, mixture number 2, should equal the final mixture. And the reason I'm kind of setting it up like this is because I want to make a chart of the fact that in my solution I have a volume, or how much it is, right, to use the chemistry word, and the concentration, which refers to the percentage. So this is really the amount, and this is the percentage. Okay. The first mixture, it says that the container currently has 120 grams of a 40% salt solution. How can I represent 40% as a fraction? Because rational equations is all about fractions. I would say this is 40 over 100. Okay? You'll see why it's beneficial to do that in just a moment. And you'll also see why it's beneficial to not reduce. How many grams of a 10% salt solution must be added to that? So I don't know how many grams must be added to that, right? To obtain, and this is 10% solution. How many grams of a 10% solution must be added to the first thing to produce a 25% salt solution? Well, the immediate thing that's a little tricky about this problem is the fact that it looks like I have an extra unknown here. And that is almost true, right? If I have 120 grams of this, how many grams of this, that's an obvious spot to put the X, must be added to obtain, well, how many grams are going to be there? Oh, wait a minute. Just ask yourself, well, if I have 120 grams of this and I mix together X grams of this, then doesn't it make sense that your final mixture would be the 120 that you started with plus the X that you mixed together, right? If I told you that I would have to mix 10 grams of this solution together with this one in order to make this, well, then shouldn't my final mixture have 130 grams? That's my 120 plus the additional 10. Hopefully that makes sense. So now what you can do is you could say, well, this times this plus this times this should equal this times this. You're saying that your 120 grams of a solution that's 40% salt mixed together plus your X grams mixed together with your X grams of a 10% salt solution should equal 120 plus X grams of your 25% salt solution. Okay. you're going to notice why it's beneficial to not reduce those fractions in just a moment. I appreciate you hanging on a couple extra minutes. If I multiply here, 120 times 40, that's going to be 4,800 over 100 plus 10x over 100 is equal to, a little distributing here, I have to do 120 times 25 in my calculator. We get 3,000 plus 25x all over 100. The reason why at the very start of my problem it was beneficial to not reduce is the fact that now all of our denominators match up already. If you reduced, think if you made this 4 out of 10 or 2 out of 5, and you made this 1 out of 4 and made this 1 out of 10, well, now you'd have to find your least common denominator all over again. So by leaving everything out of 100, it prevents that from having to occur. Now you're just left with an Algebra 1 problem where you'd say 4,800 plus 10x equals 3,000 plus 25x. And now you can solve from there. You can say, well, let's subtract the 3,000 to this side. We get 1,800 and move the 10x over here. So I'd say equals 15x. And divide by 15. Over 15. We get 120. So that means 120 grams must be added to it, the same amount. Actually, if you notice, 25 is directly in the middle of 40 and 10. And that would mean that my final mixture would have 240 grams total. Okie doke. Sorry for keeping you a couple extra minutes today, but I think it was important to finish one of each example with you, or one of each style of problem. We did a distance, rate, and time problem where we identify which is the same, find the other two factors, and solve our equation. We did a work done problem where we figure out each thing's rate per day, each person, thing, machine, animal, whatever, and then their time contributed. Multiply them together and add them to equal 1 because 1 represents one whole task completed. And then we solve by finding my least common denominator. And lastly, we did a solution and mixture problem where you recognize that the first mixture plus the second mixture is going to equal the third one. If you have this much of the first one plus this much of the second one, you should get that much of the third one. And that's exactly how we set up our equation here. Okay? I will most definitely be going through more word problems and examples of these next class. Like I said, I will post some practice problems for you to try on your own if you want to try that. I will also send out the PA on word problems. That PA on word problems is not due until next Sunday night. Okay, so don't feel like you have to work on it now, but the reason why I'm getting it to you now is so that if seniors want to get a head start on it and get it done, or anybody, not just seniors, but you certainly can do that. Okay. But again, I'll provide some practice problems with solutions for you on Classroom. And other than that, that is all I have for you today. So I really appreciate you sticking around a couple extra minutes. Hopefully it was helpful and enlightening. But I will see you next on Thursday. I promise I won't go over the time on Thursday. So thank you, everyone, and enjoy the rest of your day. Bye, everyone.